Hey folks, this is lesson 9 in which we're going to start to interpret the velocity and acceleration terms when we're expressing that in the polar frame, which we covered in lesson 8. First, let's do just a quick review. What we've got here is what we've done since the first week, in which we have an inertial reference frame. We have our point P, in which we're tracking with a position vector. And in this inertial reference frame, we've defined the basis E1, E2, and then, of course, E3 is coming straight out of the plane here. Now, to apply Newton's second law to this particle, we need to obtain an acceleration in the inertial reference frame. And so far, we've done that several different ways, and that's what we'll cover really quickly here. The first way we did it is we said we'll use Cartesian coordinates. And with Cartesian coordinates, it's simply x dot, y dot on these coordinates, x double dot, y double dot in acceleration in this basis vector. Now we decided pretty quickly that anytime we have anything with rotation, Cartesian coordinates really don't give us any insight whatsoever. The equations of motion that we develop are really kind of nasty, and so we abandoned that pretty quickly. Then we moved on to polar coordinates, and with polar coordinates, really, the expressions here are not getting much better. In fact, they're getting worse for our velocity in the inertial reference frame, as well as our acceleration in the inertial reference frame. And so the advantage here was that once we got to our equation of motion, and in our example of our simple pendulum, once we got to our equation of motion, we ended up with something that was really easy to interpret. On the simple pendulum, it was theta double dot is equal to negative g over L sine theta. Okay, really nice equation of motion. That wasn't the case with our Cartesian coordinates. But we had to express our kinematics, our velocity and our acceleration, in a really difficult manner, and in a way that is just really difficult to interpret. Okay, and here I should point out, just to remind you, that these are equivalent and these are equivalent. Okay, these are equivalent terms expressed in different coordinate systems. Then we moved on to the polar frame, and we introduced this in the last lesson. In the polar frame, we're simply defining a brand new reference frame. And this reference frame, we'll call it reference frame B in this case. It's defined by the basis vectors E sub r and then E sub theta. And then this reference frame is rotated, or even rotating, with respect to the inertial reference frame. And so the basis vectors, they share a basis vector, these two reference frames. They share a basis vector that points, in this case, out of the page, which was E3 in the inertial reference frame, and we called it EZ in the polar frame. And the advantage of the polar frame was that we could get very nice looking velocity and acceleration equations, and then we ended up with this very same equation of motion. So the mechanics of this and using this is actually easier. So let's take a look at those pieces. Let's look at these kinematics, the velocity and the acceleration. And I said that they're pretty nice, and that's really what today's lesson is all about. Right now, if you look at these and you see the r dots, the theta dot squareds, theta double dots, they look a little bit intimidating, perhaps. But by the end of the lesson, we're going to have to find each contribution that each of those components has. And before we get started, I should say that if any of these equations are unfamiliar or you don't know exactly where these have come from, then revisit lessons 6, 7, and 8, in which we not only derive these, but we explain all these different parts and exactly how we get there, the advantages and the disadvantages. Alright, so let's tackle a couple case studies in which we can start to tease apart exactly what's happening in the velocity. So we'll do velocity first. And so here, for this first part, we've got just a circular path around point O. And we've defined this position vector, a position vector r of p with respect to O. And remember, from day one, when we talked about what a velocity is, we said that it's this change in this position vector. If this is p at time t, and then our our particle moves, or our point moves, at p at times t, plus delta t. And as we take delta t to 0, as that limit approaches 0, then it's this vector between these guys that's our velocity vector. Okay, so this would be our velocity vector in the inertial reference frame, because that's the only reference frame that we have here, if we express it that way, of p with respect to O. And so as this time decreases to delta t, then what we see is that, and I'll erase this next part, but as delta t goes to 0, then this velocity vector gives us a new vector. And so it's actually a vector in which is a real vector, and so it has both a magnitude and a direction. So this point P is going to have a direction of its velocity, and you can see here that, you know, if this point P is rotating in the counterclockwise direction, the velocity should point in that direction. Also, if it's in the clockwise direction, that velocity is pointing in the opposite direction. Now let's add a polar reference frame to this problem. And so here we see the polar reference frame, in which we've defined an axis that goes from the origin of the reference frame. This would be reference frame B with an origin of O, basis vectors E sub r, E sub theta, and E sub z. And so one axis going from the origin to point P, or through point P, the other axis going at a 90-degree angle to that within the plane. And so our E sub r vector is pointing to the point, our E sub theta vector is pointing in positive theta, as we've defined last time. And we've also introduced polar coordinates to this, in which we have r being the radial distance from the origin to the point, or the absolute distance really from the origin to the point, and then theta being the angle at which this reference frame B is rotated with respect to reference frame I, the inertial reference frame. And so with our new reference frame on here, and with our basis vectors E sub r and E sub theta, let's take a look at this velocity equation of point P with respect to O, expressed in the E sub r and E sub theta directions in our polar frame. And so our first term here, we see it's r dot in the ER direction. Now, on a circular path around point O, then r dot is going to be equal to 0. So if r dot is equal to 0, then that means we shouldn't have an E sub r component. And in fact, what we're seeing here is that E sub r, going from point O to point P, there is no component in that direction. But we do have a component in the E sub theta direction. And that's the only component that we have on the circular path. And this is a magnitude. The magnitude of this velocity vector is r theta dot in that direction. Now, the E sub theta direction, when you're on a circular path, you can see is always tangent. It's going to be tangent to that path. And so this is just a property of velocity in general, is that velocity is always going to be an expression in which gives us the tangent of the path. You're going to see this pop up in path coordinates that we'll do next lesson. And that gives us our direction, and our magnitude is always going to be the radius of the path, or the distance away, multiplied by the angular speed. But we don't want to be confined to just a single radius, because that gives us only a circular path that we can use. And motion, any motion is much more interesting if we can get out of just spinning around in a circle. So let's examine a velocity expression in which we do have a changing radius. So that would mean that r dot, where r dot is not equal to 0. And so the example that we'll use here is this of a spiral. And you'll see that the radius, it starts out at 0 and then increases throughout the motion of the mass. And then what we see here is that in our velocity, our inertial velocity expression, is that we have an ER component and we also have an E theta component. So let's draw these in. So for our ER component, we're going to have a magnitude of this vector, and this is going to be r dot. And so hopefully this makes good sense, because if r is changing and r has a time derivative, then the point itself is going to have a time derivative that's moving out radially. So for instance, if we're not actually spinning and we only have motion in this line, the velocity of this point P is going to be defined simply by a vector in this direction, in the ER direction, that is the speed, or the change in speed, of that radius r, or of that length r. Now likewise, we have a component in the E theta direction. And so if we draw that vector, the E theta, which is 90 degrees to ER, then this component is r theta dot, just like last time. Now if we draw these two together, then we should get a resultant that's made up of the ER direction and the E sub theta direction, and this resultant itself is the velocity of P with respect to O. Now I didn't draw this quite to scale as well as I could, because this ER should be much shorter, but we still see here that this velocity, this resultant velocity, made up of these two components in the ER and the E theta direction, is tangent to the curve. And so that's going to be true whether we're at the bottom of the curve, here, here, here. Velocity is always tangent to the curve. And in the polar frame, we now have two different directions that we can make that velocity up, and we can interpret them. We have the radial velocity, which is in the ER direction, and then we have this the circular velocity, or the E theta direction. Alright, so let's see what we can do with acceleration. And we'll start, just like what we did with velocity, in drawing this out and doing the geometric representations of these vectors. So we just now established that velocity is always going to be perpendicular to the radius, or tangential to the path. So that means that at this time point we have a velocity of p, and that would be what that vector is. And so let's say we've got another time, and there's our velocity. There's our new velocity. This is v at, say, t plus delta t. So this would be at t in the inertial reference frame. And so you can see that velocity is always going to be tangent to the path, but it can also change length. So if we do the same thing to define our acceleration as we did with velocity, which is looking at the change in velocity as delta t approaches 0, then as delta t approaches 0, we could draw these two velocities. So there's our v sub p at t, and then our next velocity being v sub p at t plus delta t, right? Then our acceleration is going to be the vector between them. So there's the acceleration of point P. And so if we draw that now at this time, then we're going to get an acceleration vector. Let me draw that the same. So we're going to get an acceleration vector that looks like this. So our acceleration of point P in the inertial reference frame with respect to O, point O. Now notice here that acceleration doesn't have the same constraints on it that velocity does. Acceleration is not always tangent to the path, and that's a key distinction between velocity and acceleration. Velocity is always tangent to the path. Acceleration is not tangent to the path. Alright, so let's get rid of these velocity vectors, because we're okay with that. And then let's examine the acceleration in the polar frame. So here's our polar frame. Just like before, we've got an E sub r, we've got an E sub theta, and we're calling this reference frame B. Now, here we're on a circular path in this case study, because we're saying that we're fixing this radius, so that means that r dot is equal to 0, and also r double dot is equal to 0. There's no acceleration along this radial direction at all. We only have, oh, I'm sorry, there's no speed, change in speed, or change in change in speed or change in position of this this component. So let's start with the E sub theta, and let's work our way through that. So if we've said that r dot is equal to 0, then that means that this term we can just say is equal to 0. And if we're only moving around a circle, the only thing that we have in the E theta direction, and so the E theta direction being this direction, which is tangent to the circle, is going to be this term r theta double dot. So let's draw that on there. This is our only component, r theta double dot. And this r theta double dot is tangential to the path, and so it's similar to what we saw in velocity. So, or in our velocity, in which that was a change in position. So here, this r theta double dot is representing a change in speed only. And because of the direction that it's pointing, which it's pointing in the direction that this particle is moving, it's telling us that this particle, as it's moving around the circle, is speeding up as it goes, and that's the theta double dot. Okay, it's related to that angular acceleration. And so you can see that here in how we drew our velocity vectors, because at time t, the velocity was a particular length, and then at time t plus delta t, we see that we drew our velocity vector at a longer length. And so you can see that v of our particle at t plus delta t is greater than our velocity, our magnitude of our velocity at time t, and because of that we're going to have a positive acceleration, or this change in speed is going to be pointing in the direction that the particle is traveling. And so likewise, if this weren't true, let's say this were opposite of each other, then the direction would be r theta double dot, but it would be decelerating and it would be pointing in the opposite direction. Now let's take a look at the E sub r direction. And in the E sub r direction, okay, we have an r double dot minus r times theta dot squared. Now we've already said that in this case we are only traveling in a circle, so as a result this radius isn't changing, so we'll just set that equal to 0 in this case. But now we have this term that's a negative r multiplied times theta dot squared. And so the negative indicates that it's in the opposite direction of E sub r, and so the opposite direction of E sub r is going to give us an acceleration vector here, and it has a magnitude of r theta dot squared. And so first off, you can see those are our two components that give us our acceleration that we had mapped out, our acceleration vector that's pointing inward, and then in the E sub theta direction, because it's speeding up, and inward because of this r theta dot squared term. Now this r theta dot squared term is always going to point in the middle. That's why it's always a negative sign. And you can see it's always going to be pointing that direction, because theta dot, whether it's positive or negative, is going to be squared, and then r is always going to be a positive value. So what this is representing, we've already said that this r theta double dot is telling us about our change in speed, is the change in magnitude of each of those vectors. But acceleration is not only a change in speed, but it's also a change in orientation. In this case, a change in direction or a change in orientation of these vectors. So you see that v sub p at time t is pointed in one direction, and v sub p, our velocity at time t plus delta t, is pointed in a different direction. And this has to happen if you're on a curved path, okay, which we showed before, that your velocity, okay, is going to be tangent there, it'll be tangent there, it'll be tangent there. So you can see that this velocity vector is always going to be changing. And so in summary, there are two things that can cause an acceleration. One is a change in speed, and then the other one is a change in direction. And so anytime we have something that's moving on a curved path, then it's going to be accelerating even if it's moving at the same speed along that curved path. Now let's put this into Newton's second law, and let's observe some interesting effects about these forces. So Newton's second law says that the forces on a particle, all the forces on the particle, are equal to the mass of that particle, or of that point, multiplied times the acceleration as observed in an inertial reference frame. So all of our forces in this case, we can take our forces in two different components. We've got an F sub r in the E sub r direction plus an F sub theta in the E sub theta direction, and that's multiplied times the mass, and that'll be r double dot, or it's equal to mass multiplied times r double dot, r theta dot minus r theta dot squared in the ER direction plus the mass multiplied times 2 r dot theta dot plus r theta double dot in the E theta direction. Alright, we got rid of these guys because r double dot is equal to 0 in this case, and r dot is equal to. And so what we see here is that the force in the theta direction has to be equal to mr theta double dot. And this fits well with Newton's first law, because we're saying that if we're going to change our speed, if we're going to increase the speed, then we have to do that with a force. And so that's exactly what Newton's first law says. It says if a body is in motion, it's going to stay in motion with a constant speed unless acted on by another force. Next, when we equate these pieces, we get an F sub r, and F sub r is going to be r theta dot squared. And so what this is saying is that in order to maintain a trajectory that's a curve, there has to be some sort of force that's changing the direction. And this is simply a constraint force, okay? And so what this force is doing is it's actually a reaction force. Now, it sort of begs the question, okay, it's a reaction force, but it's a reaction force to what? And this is where this idea of a fictional force comes into play. Because this acceleration, this r theta dot squared, that's pointing inward, okay, that's telling us about how it's curving along that path. And this is called a centripetal acceleration. The centripetal acceleration points inward, and there's a fictional force that we call, it's not a real force, but we call it the centripetal force. And so we've all experienced this before, where an example is, say you're riding in a car and you're in the passenger side and the driver turns to the left. And if the driver turns to the left, then there's this feeling that you're being pushed to the door. You're being pushed to the outside of the car. And so that's a fictional force. And it's due to the fact that you're traveling in a straight line, and your body wants to remain traveling in that straight line, just like Newton's first law. And then you're acted upon to turn. Now, you stay along that curved path because you stay in the car. And so this force is what keeps you in the car that we see right here, because it's reacting against that fictional force. And that's essentially the force of the door. You're traveling in a straight line, and then the door turns in front of you and then keeps you on that curved path. So the centripetal force is a fictional force. It's something that you feel, it's something that we've all experienced before, which is trying to push you to the outside of a curve. But the reason why you stay on the curve is due to this force that we see here, that we've just made with Newton's second law, and that's a constraint force. Now, something that's interesting is that these fictional forces do not occur in an inertial reference frame. Okay, so if you're in the car and you're traveling, your reference frame, and you're traveling around a curve rather, your reference frame is not inertial. And so because you're rotating, a rotating reference frame is a non-inertial reference frame. And it's in non-inertial reference frames where something is accelerating, because rotation is an acceleration because it's changing path, or accelerating, let's say linearly, is a non-inertial reference frame. And that's where we get these fictional forces. So in order to have a fictional force, you need to be in a non-inertial reference frame. Okay, you're going to see forces, or you're going to experience forces that don't really exist. But if you observe it from an inertial reference frame, it makes perfect sense because you've got all that information. All right, so now let's move to non-circular motion. And in non-circular motion, according to our acceleration equation, r dot is now not equal to 0. We'll say that it's in the spiral where actually r dot is greater than 0. And then just because we're on a spiral doesn't necessarily mean that r double dot, or the change in that radius or the change in that distance from O to P, is accelerating. But in this case, let's say that it is. Okay, so we've got a spiral, and we're not only just moving at a larger radius, but we're also speeding up as we do it. All right, we've got all of our components here. Let's take a look at the E sub r components first, that magnitude, and we'll see that we've got, if r is changing speed, okay, then r double dot is greater than 0 or less than 0, and so we're going to get a component that if r double dot is greater than 0, that we have a magnitude here that's pointing in the ER direction. Okay, so that comes out of the first term. Our second term we've seen before. This is our centripetal acceleration, and our centripetal acceleration is always pointed in, and this is based on, as we said, it's based only on the distance away from the origin, or the radius of curvature, and the fact that it's rotating, so theta dot squared. It has nothing to do with the fact that this might be accelerating in and out. Okay, so we have our centripetal acceleration always pointing in. We have our r double dot, which is our radial acceleration, which is pointing out if that's an increasing rate of speed, or pointing in if it's a decreasing rate of speed. And then as we look in the E theta direction, okay, let's do our easy one, in which we have a tangential component here. Well, I'm sorry, not tangential component, but we have our change in speed, or change in rotational speed, r theta double dot. And so these are all the things that we've dealt with so far. But we've still got this guy right here, which is 2r dot theta dot, and this is the weird one. So to start out, let's just take it at face value. What we're saying here is that this term in the acceleration, which we call a Coriolis acceleration, is twice the magnitude of the change in the radius, r dot, and the change in the angular speed, and the change in position, theta dot. And it's pointing in the E theta direction, E sub theta direction. So I'll put this in red, and this is 2r dot theta dot. So let's put this in the context of something that we know. Okay, we've got a good idea. I think that we all have good intuition about what's going on with this centripetal acceleration. Okay, we've felt that before. Like I said, if you're going around a curve, you know what that fictional force feels like. You know what it's like to be constrained to stay on that curve. Okay, and so what we can do is, because that's actually a big effect, one that we experience quite a bit, we don't actually experience or recognize that we experience that Coriolis acceleration that much. And part of the reason why is because of the magnitude in which this occurs. So r theta dot squared, that magnitude, is oftentimes quite a bit larger than this 2r dot theta dot. And a lot of that's because of this squared term. Okay, so we're going to experience that acceleration. We're going to feel that fictional force much more easily than we feel this Coriolis acceleration. Now, that implies, though, that this 2r dot theta dot, you're going to experience a fictional force, even if the effect might be subtle in daily occurrence, simply because the magnitude's small. So let's talk about when you may have experienced this. Let's say you were on a carousel at some point, and so you were standing about here. So that means that if you're on the carousel and you're just standing at that point, you're rotating around and around and around. We'll make that counterclockwise because we've got a rotational speed that's going counterclockwise. And so you're just going around and around and around and around counterclockwise if we're looking at it from the top. Now, in this context, you've got a centripetal acceleration. If you're standing at this point here, then that means that there's a fictional force that's attempting to push you to the outside, and the reason why you're not moving is because your feet are planted on the ground and you're creating a constraint force by that connection to the carousel that's keeping you on that path. Okay, so that's the fictional force of the centripetal acceleration, and then that centripetal force. And important to note here is that your velocity is always going to be tangent to that path in which you're staying. But what happens when you decide you want to move from this spot and move toward the outside of that carousel? And so you want to take a path that looks like this. If you've ever done that, you've tried to take that step, it's hard to do. Okay? It's like there's this force that's knocking you sideways. Well, that's the Coriolis force. It's a fictional force that is actually trying to knock you sideways. And here's the reason why it happens. You see, when you take a step, and you take a step out in this direction, okay, outward, then what you're doing is that the inside of the carousel has a particular velocity. But as you move out here, then this part of the carousel actually has a larger velocity, or a larger speed rather. And so that is a change in speed. And so because of that change in speed, that gives us this term, in which we say that we have 2 r dot theta dot is equal to, and in this case it's going to be our r dot multiplied times the time derivative in the inertial reference frame of theta. And so that's our change in speed, because where you step, remember, you step right here onto a part that's actually moving faster than where you were. Now, that's just one part of it, because when you step on that point, when you step on that spot right there, not only are you changing speed with a longer magnitude of that velocity vector, but this velocity vector itself is changing directions. And so that means that your direction in that ER is also changing as well. So this direction that you're attempting to move is also changing directions. And so that gives us our second component of the Coriolis acceleration. And so those two pieces now give you this kind of strange acceleration, which is trying to knock you off your feet whenever you're trying to move, like I said, either outward or inward. And it's proportional to the speed that you're moving outward or inward. So if you try to go really fast, then that fictional force is going to feel that much harder. Okay. Likewise, if the carousel, okay, if your rotating body here is moving faster, it's going to be much more difficult to do. And so in summary, what's happening here is that you may think that you're actually trying to walk out, but what's actually happening is that your path is this curved path. Okay, it's this curved path just like that. And so when you try to do that, it's difficult to do, and for you to stay on that path, it's going to take some extra constraint forces. So when you step forward, unless you've already prepared to apply that extra constraint force, because it's actually possible to do if you anticipate, what that acceleration is going to do in knocking you off your feet. So most likely this is the example that probably resonates most with you, but also Coriolis acceleration comes into play on a big scale. And so on weather patterns, okay, it gives us the direction. Okay, if we've got the Earth and we've got a a weather system, okay, that's why our weather systems move in the directions that they do. And why in the northern hemisphere our storms rotate counterclockwise, whereas in the southern hemisphere the storms rotate clockwise. And so this is an important point to make, because that's due simply because of the rotation of the Earth around its axis. In addition, this affects ballistics. So if you've got long missiles, for instance, you need to account for the Coriolis acceleration, which is essentially the rotation of the Earth underneath a trajectory motion or a ballistic. So in summary, we've got some great tools now, and more importantly, tools that make sense. Because remember, we can get our answers in lots of different ways, but the polar frame is particularly unique because we're defining these directions, okay? And by defining these directions, it gives us insight on what these velocities, these two components of the velocity, as well as these four components of the acceleration, actually mean, and give us interpretability. Whereas if we put everything in the inertial basis, then we really had some issues there regardless of what coordinate system that we used, whether it was a Cartesian coordinate system or whether it was a polar coordinate system. All right, I'll see you in class.